Today we'll be continuing our discussion about vector functions. So after limits and continuity, we will now be proceeding with derivatives and integrals of vector functions. So let's start with derivatives. The derivative r prime of a vector function r is defined in as much as the same way as for real valued function. That is, dr over dt, which is r prime of t. It is the limit of r of t plus h minus r of t all over h. And this is to be evaluated as h approach 0, if this limit exists. So the geometric significance of this definition is shown in the figure. So we can have the secant vector p going to q, which is the limiting value for the tangent vector r of t. If the points P and Q have the position vectors r of t and r of t plus h, then PQ represents the vector r of t plus h minus r of t, which can therefore be regarded as the secant vector. If h is greater than 0, a scalar multiple of 1 over h times r of t plus h minus r of t has the same direction as r of t plus h minus r of t. As h approaches 0, it appears that this vector approaches a vector that lies tangent on the line. For these reasons, the vector r prime of t is called the tangent vector to the curve defined by r at the point P, provided that r prime of t exists and r prime of t is not equal to 0. The tangent line to C at P is defined to be a line through P parallel to the tangent vector r prime of t. So, we can have the derivative to represent the direction vector. The following theorem gives us a convenient method for computing the derivative of a vector function r. Just differentiate each component of r. If r of t is composed of f of t, g of t, and h of t, then we have f of t I, g of t j, and h of t k, where f, g, and h are differentiable functions. Then r prime of t would just be the derivative of f of t, which is f prime of t, the derivative of g of t, which is g prime of t, and the derivative of h of t, which is just h prime of t. So we will be having f prime of t I, g prime of t j, plus h prime of t k. A unit vector that has the same magnitude or the same direction as the tangent vector is called the unit tangent vector t and is defined as, so the tangent t is equal to the derivative r prime of t, and we divide it by its magnitude r of t. Let us find the derivative of r of t, which is equal to 1 plus t cubed I, t e to the negative tj, and sine 2t k. So we have f of t is equal to 1 plus t cubed. So f prime of t would be 0 plus 3t squared. So this would be your x component. For the second part, g of t, which is t e to the negative t, so g prime of t is the derivative of a product, t e to the negative t times negative 1 plus e to the negative t times 1. So that would be e to the negative t times negative t plus 1, or simply 1 minus t e to the negative t. And with h of t equal to sine 2t, so h prime of t is 2 cosine 2t. So that would be the third component. With this, we evaluate this at t equal to 0. So it would be 0, 1 minus 0 e to the 0, so that would be 1, and then 2 cosine 0, so it would be 2. So we are having r prime of 0 is 0, 1, 2. So we find the magnitude of this, square root of 5, would be square root of 0 squared plus 1 squared plus 2 squared, square root of 5. So we divide the derivative 0, 1, 2 by square root of 5. So we have the unit tangent. So after dividing 0, 1, 2, 0i plus 1j plus 2k by square root of 5, we will be having I over 0 over square root of 5, I, 1 over square root of 5j plus 2 square root of 5k. Just as for real valued functions, the second derivative of a vector valued function or vector function r is the derivative of r prime. That is, r double prime is the derivative of r prime, so r prime prime. For instance, the second derivative of the function r of t is equal to 2 cosine t sine t. T is, so we have r is 2 cosine t sine t and t. So f is 2 cosine t. So f prime is negative 2 sine t, and f double prime is negative 2 cosine t. For g sine t, so g prime is cosine t, and g double prime is negative sine t. For h, we have t. H prime is 1 and h double prime is 0. So we have negative 2 cosine t, negative sine t, and then for the third component, 0. For differentiation rules, the next theorem shows that the differentiation formulas for real valued functions have their counterparts for vector valued functions. Suppose that u and v are differentiable vector functions, and c is a scalar and f is a real valued function. Then so the vector valued function is a linear differentiable function, so we can apply linearity. So the derivative of u of t plus v of t is u prime of t plus v prime of t. So we can differentiate u and v separately. If we have a constant multiplied to the function, so you can factor out constant and then differentiate u of t. So this is the linearity property. If we have a product of two functions or two vector valued functions, so it also follows the derivative of uv, which is u dv plus v du. So f prime of t, u of t plus f of t, u prime of t. For the derivative of the dot product, so it also applies product rule. So the derivative of the dot product of u of t and v of t would be u prime of t dotted to v of t and u of t dotted to v prime of t. For the cross product, the derivative of u cross v is equal to u prime cross v plus u cross v prime. While for the derivative of composite function, so we apply chain rule. So the derivative of u of f of t would be the derivative of u, which is u prime of f of t, times the derivative of f of t, which is f prime of t. So we use the formula 4 to prove the following theorem. If r of t is equal to constant, then r prime of t is orthogonal to r of t for all t's. The proof is, since r of t dotted to r of t is equal to r of t squared, which is equal to c squared, and c squared is constant. So for formula 4 of theorem 3, it gives 0 is equal to the derivative of r of t dotted to r of t. So that would be r prime of t r of t plus r of t times r prime of t, which is equal to 2 times, so since they are the same, so it would be 2 times r prime of t dotted to r of t. So thus, r prime of t dotted to r of t would be equal to 0, so which says that r prime of t is orthogonal to r of t. So again, if the magnitude of r of t is a constant, so then r prime of t is orthogonal to r of t for all t's. Geometrically, this result says that if a curve lies on a sphere with center at the origin, then the tangent vector r prime of t is always perpendicular to the position vector r of t. So the radius is perpendicular to the tangent line. Now let's proceed to integrals. The definite integral of a continuous vector-valued function r of t can be defined in as much as the same way as for real-valued functions, except that the integral is a vector. But then, we can express the integral of r in terms of the integrals of its component functions f, g, and h as follows. So the integral of r of t dt from a to b is the limit of r of t times delta t from I is equal to 1 to n for n is as n approach infinity. So this is the Riemann sum, the definition of definite integral for functions. So we just integrate, or we just take the summation for all of these small rectangles as your delta t approach 0 and your n approach infinity. So the integral of r of t dt from a to b would be the integral of the first component f of t dt from a to b plus the integral of g of t dt from a to b plus the integral of h of t dt from a to b. with their corresponding unit vectors I, j, and k. So this means that we can evaluate an integral of a vector functions by integrating each component function. We can extend the fundamental theorem of calculus to continuous vector functions as follows. The integral of r of t dt from a to b is equal to the antiderivative r of t evaluated from a to b, which is r of b minus r of a. That is, if we're going to differentiate r of t prime, r prime of t, it would be r of t. So we use the notion r of t dt for indefinite integrals. If r of t is equal to 2 cosine ti plus sine tj plus 2tk, then the integral of r of t dt would be equal to the integral of 2 cosine t I. So that would be 2 sine t. And the integral of sine t would be cosine, negative cosine. And the integral of 2t is t squared. Plus a vector constant c. So take note that this is a vector constant. It would be a constant for each of the component. So c is a vector constant of integration. And if we plan to integrate this definite, if we want to find the definite integral of r of t dt from 0 to pi over 2, so we evaluate it from 0 to pi over 2. So that would be 2 sine pi over 2 minus 2 sine 0. And then for the second component, negative cosine pi over 2 minus negative cosine 0. And then we have pi over 2 squared minus 0. Sine of 90 degrees or pi over 2 is 1. So we have 2. And then negative cosine pi over 2 is 0. Cosine 0 is 1. And we have pi squared over 4. So we have 2, 1, and pi squared over 4. So that's all. Thank you for watching.